Hello and welcome to Textbook Engineering Problem. Today we're working out of Chemical Engineering Processes, 3rd edition. We're doing problem number 5.32. Sorry, I've been gone for a while. Had a bunch of personal things going on, graduating and moving a few times, starting a new job, and having a new addition to the family and things like that. So anyway, a bunch of things going on. I'll try and get to these, but it's pretty hard to do all of the things all at once, right? So yeah, the videos have been slow to update. So anyway, thanks for joining me on this problem. I'll try and get to all of your guys' comments eventually. Hopefully, if it doesn't help you, hopefully it helps the next person that comes along that has to do the same problem. Anyway, I just recorded this video. I'm going to complain to you guys. I just recorded this video and did everything and then realized that I didn't have the audio. So if I sound grumpy, it's because I'm redoing the problem. Anyway, with audio this time. So you guys don't just see like random highlights popping up on the screen with no explanation. Anyway, let me get to this problem. The oxidation of nitric oxide is NO plus 1/2 oxygen gas. Yeah, that equation, and O2. Okay. It takes place in an isothermal batch reactor. That means the temperature is constant. The reactor is charged with a mixture of 20 volume percent nitrogen oxide and the balanced air at an initial pressure of 380 kilopascals absolute. Okay, part A. Assuming ideal gas behavior, determine the composition of the mixture, component mole fractions, and the final pressure kilopascals if the conversion of nitrogen oxide is 90%. Okay, so we're starting off, say it's ideal gas, PV equals nRT. Okay, we know that total number of moles is equal to the addition of all the components. This one's a little bit tricky because they don't give you the volume, they don't give you the temperature, right? But they don't give you those things because you don't actually need them. You just keep them in the problem as variables V and T until they eventually will just cancel out because you don't need them. They're not important for solving what they asked you to solve. That happens very frequently with the ideal gas law. If you start using more complicated equations of state, that's not the case. Okay, so then you will need to know the volume and the temperature and things like that. But ideal gas law makes things nice that a lot of things just end up canceling out. Anyway, more than you probably needed to know. First things first, we started off with nitrogen oxide. The initial amount of moles is equal to this, okay? 0.2 times the volume and 0.8 times the volume for air. We need to split that up into oxygen and nitrogen, okay? And we do that here. Okay. So then we plug in all of the variables into this equation. PV over RT just ends up canceling out, okay? And you end up with your mole fractions corresponding to each of these values, okay? So that's what those mole fractions are. That's the initial thing that they asked us. Okay, the second part they asked us is to calculate what P2 is, okay? In order to calculate P2, we have to know the conversion because as you convert, you're changing 1.5 moles into 1 mole. Okay, so your pressure is going to what? Decrease over time. As you convert more and more, as the reaction goes this way, you decrease the number of moles, your pressure is going to go down. Okay? Okay, so they give us the conversion of NO. Okay, so we'll convert that into a relationship between the final number of moles and the initial number of moles. Then we can use that information to calculate what the extent of reaction is. This is the general extent of reaction equation. We apply the general extent of reaction equation to each of the species, okay? So we'll first use this equation that they set up to calculate what the extent of reaction is, and then we'll apply it to each of these equations. Okay, so we start off, we get an extent of reaction, and we put it in terms of N1, okay? So you can see, you can follow this math, how we put it in terms of N1, okay? Then we do the same thing for number of moles of oxygen. Put everything in terms of N1, okay? Then number of moles of nitrogen, put it in terms of N1. Number of moles of nitrogen oxide. We did it kind of up here, but we didn't have it in terms of N1, so I'm just putting it in terms of N1 over here, okay? And then the same thing for nitrogen dioxide, put it in terms of N1, okay? Now that we have everything in terms of N1, we add everything up. That's the total number of moles at equilibrium, okay? N1's factor out, we add everything up, we get that N2 is equal to N1 in this ratio, okay? So now we have pressure 2 equals N2 RT over V, right? We can substitute in what we got. N1 RT over V equals P1. We know what P1 is, okay? Calculate what the pressure is. There you go. That's P2. Okay. Part B, suppose the pressure in the reactor eventually equilibrates, levels out at 360 kilopascals. What is the equilibrium percent conversion of nitrogen oxide? Calculate the reaction equilibrium constant at the prevailing temperature, Kp in atmospheres, okay? That's something we need to watch out for because they gave us pressures in kilopascals. Defined as the equilibrium constant, yes, okay, so where partial pressure is in atmospheres is the partial pressure of species I at equilibrium. Okay, don't you wish we had just used variable C when we were calculating the extent of reaction earlier? Then we could have just plugged in a new conversion percent. Instead, we have to redo everything at a new conversion percent. And so we do the exact same thing, and then we just solve for C backwards instead of using it to solve for an extent of reaction, using C to solve for an extent of reaction. Now we just use C as a variable and solve for an extent of reaction and just put it in terms of C. Okay, so now everything's in terms of C, and then at the very end, we'll just solve for what C is. Okay, so we start off with partial pressure. We have this pressure ratio. Okay, so that means N2 equals this ratio times N1. Okay, and then we have our same conversion here. We just keep it as C instead of as 90 or 0.9. Okay, we get our extent of reaction. Extent of reaction is there. Okay, I did this one a little bit faster because we just did this, but now everything's in terms of C. Okay, so we're just using the exact same thing, extent of reaction equation. We just put it in terms of C. Okay. Then you add everything up. You have this big old equation, but it's a function of C. All the N1s cancel out. You have a new ratio here that they gave to you because they changed what the pressure was, right? So make sure you change that. And then you can, it's an algebraic equation, one variable, you just solve for what C is, okay? So C equals this. Now we go to our partial pressures. Partial pressure is equal to, well, if you're using the ideal gas law, it's equal to this, okay? Which means that the partial pressure is equal to the total pressure times the mole fraction, okay? So total pressure times mole fraction, total pressure times mole fraction, total pressure times mole fraction. Okay, you'll see that these total pressures cancel out, but this one does not, and that's why our answer is in terms of 0.5, minus 0.5 atmospheres, right? So make sure you convert this pressure into atmospheres, and we just calculate what our mole fractions are because we know what our total mole components are, and we know what N2 is equal to, okay? So Xi is equal to Ni over N, okay? That's how you convert, that's how you make a mole fraction. So then you just put this in terms of N1, the N1s cancel out, and we plug in what C is. Obviously, we know what C is now, so then we just calculate what those are. We get that our component mole fractions are that. You just plug them into this equation, make sure you convert your pressure into atmospheres, okay? And then you get the equilibrium constant. All right, well, that's it for this problem. Let's see, Oh, yeah, I have to let you guys know that, like I said, I'm gonna try and get to your other requests. Thanks for sticking it out, holding out for the answer here. Hopefully, it was helpful for you. Hopefully, I haven't missed the window on that. I'll try and pump out the rest of your requests here. Remember that there's a bunch of different ways to approach these problems. You don't have to do it the same way that I did. But hopefully this gives you a good framework of how to set up the problems so that you can um, um, get used to how the math looks and get used to manipulating these variables and things like that. And as you see the different rules and pathways that I solve things, it can kind of help broaden your mind as to how math is very fluid and you can move things around to make it easier for yourself. All right. Well, hope you have a good day. I hope to see you in the next problem. Don't forget to like and subscribe. The more people that do that, the more time I'll be able to spend on these problems. All right. Thank you. Hope you have a good day.